current, voltage, resistance. Three of the fundamental properties of electricity. But how are they related? Now, according to Ohm's law, current equals voltage divided by resistance. So 1 ampere of current equals 1 volt divided by 1 ohm. Current, voltage, resistance. Each one of these properties is defined by the other two, so if you know any two, you can determine the third one. And this concept was derived experimentally. So let's do the experiment, and let's do the math, and we'll see how they compare. Welcome to Scofflaw Laboratories. We're going to look at some circuits, take some measurements, and find the unknown. In this circuit, there's a 9-volt battery and a 22k ohm resistor. Through this circuit, there passes a current. That's the unknown property. We'll get more precise measurements of the battery and the resistor, and then we'll calculate the current. And current equals voltage divided by resistance. The value by itself, in this case current, is the unknown value. We'll measure the voltage and the resistance and calculate the current. We'll start by measuring the voltage across this resistor and then the resistor itself and plug them into this formula to calculate the current. And we have 9.52 volts. We'll remove the green jumper to measure the resistance. And we have 21.84 k ohms, and k is 1,000, so that's 21,840 ohms. So we have our two values, voltage and resistance. We'll plug them into this formula. And current equals voltage divided by resistance. And when we do this calculation, it comes out to an irrational number that will round off to 0.000435 amperes. Let's take a measurement. We have 0.44 milliamps. Now Ohm's law is in terms of amperes and my meter measures in milliamps. So let's look at how we make that conversion. We measured 0.44 milliamperes, and amperes, or amps, is equal to milliamps divided by 1,000. So we take 0.44, we divide by 1,000, and we have 0.00044. Or you can just move the decimal point over 3 spaces. We divided the voltage by the resistance, and we got 0.000435 amperes. And then we measured 0.00044 amperes. That's better than 2% accuracy. I'd say Ohm's law did well here. I changed this battery to a used one, so the voltage is unknown. In the last example, current was the unknown value. That was the value by itself. Now voltage is the unknown value. So we need to get this by itself. And we can do that algebraically. Since this is division, we undo division with multiplication. So we'll multiply both sides by resistance. We multiply both sides by resistance. And on this side, resistance cancels. And we're left with resistance times current equals voltage. We'll just restate that in the standard format. Voltage equals current times resistance. So now the two values we'll measure are current and resistance. And we have 0.29 milliamperes. But as we learned before, that equals 0.00029 amperes. And the resistor is the same one from before, is 21,840 ohms. So we have our two values. We'll just plug them into this formula. And when we do this calculation, we end up with 6.3336 volts. Let's take a measurement and see how we did. We'll put that green jumper back in place. And we have 5.55 volts. We calculated 6.3336 volts, and we measured 5.55 volts. Not as accurate as last time. It's off by more than 12%. In that last example, we used voltage equals current times resistance. But now the resistor is unknown, so we need to get this value by itself. Since this is multiplication, we undo multiplication with division. We'll divide both sides by current. We divide both sides by current, and on this side, the current cancels. And we're left with voltage divided by current equals resistance. And if you'll just humor me, I like the unknown value on the left. Let's put the green jumper back in place to measure the voltage. And we have 9.54 volts. We'll remove the green jumper and measure the current. 0.15 milliamperes. And as we now know, that equals 0.00015 amperes. We have our two values, so let's plug them into the formula. Voltage divided by current. And when we do this calculation, we get 63,600 ohms. Let's take a measurement, see how we did. $63,000 ohms. We calculated 63,600 ohms, and we measured 63,000 ohms. It's better than 1% accuracy. And that, my friends, is the relationship between current, voltage, and resistance. Ohm's law models an ideal world. In actual applications, the tolerances we just saw are perfectly acceptable. And that's why after almost 200 years, Ohm's law is still revered as one of the fundamental building blocks of electronic design. This experiment was simple, and the math was pretty easy too. So just go grab a handful of parts and try it for yourself. And then come back to Scofflaw Laboratories for some more electronic basics.